Imagine you're in a high-performance, hybrid electric vehicle. You're cruising down the highway at, I don't know, 80 miles an hour.
Right.
The ride is smooth, the cabin is quiet, everything feels completely under your command. But inside the brain of that vehicle, specifically inside the dual motor controller, or what engineers call the PCS, a microscopic event is just brewing. Like within a fraction of a millisecond, a voltage transient could cascade through the system, blast thousands of amps through the silicon brain of your car, and just instantly melt its core components into slag.
It's terrifying to think about.
Right. So today our mission for this deep dive is we are tearing into a massive stack of engineering specs to find out how your car fights a microsecond war to stop an explosion that you never even knew was happening. We're looking at the single most destructive hardware failure mode in a PCS, which is the inverter and power stage overcurrent and short circuits.
Yeah, and it is genuinely one of the most brutal environments we have ever engineered electronics to survive in. Because, we're so used to mechanical failures, like a worn bearing or...
A blown gasket.
Exactly, a blown gasket. Those give you warning signs. You hear a rattle, you feel a vibration.
Right.
But an inverter short circuit is completely invisible. We are talking about the complete destruction of ASIL D safety systems. And this is occurring at the atomic and electromagnetic level faster than the human brain can even process a single thought.
Okay, let's unpack this, because ASIL D, that is the absolute highest automotive safety integrity level classification that exists, right?
Yes, the highest.
So we aren't just looking at a failure that leaves you pulled over on the shoulder waiting for a tow truck. We're dealing with literal contained lightning here. The specs in our source material indicate that during these specific inverter short circuits, the current spikes to over 1,000 amps in microseconds.
Which triggers catastrophic joule heating.
Right.
The silicon carbide, the SiC semiconductors that act as the gatekeepers for all that power.
Yeah.
They cannot physically shed that heat fast enough. The internal lattice of the silicon just breaks down and literally liquefies.
Oh, man. So how does something so catastrophic actually start? Because to understand how to stop an explosion, we first have to look at the spark.
Exactly.
And the documents detail the underlying physics of this failure mode. They break down the root causes into 4 deeply complex electromagnetic phenomena. And the first one is incredibly counterintuitive. It's called the Miller effect.
Right. So the Miller effect perfectly illustrates the double-edged sword of transitioning to silicon carbide power modules. Because SiC is revolutionary, right?
Yeah.
It allows us to switch high-voltage currents incredibly fast.
Which massively improves the efficiency of the vehicle.
Yes, exactly. But the specs note voltage changes on the order of 10 kilovolts per microsecond. And in extreme edge cases, it can hit 50 volts per nanosecond.
I am trying to wrap my head around 50 volts per nanosecond. That is a rate of change that feels almost theoretical.
It is borderline violent.
Yeah.
And that violence creates a bizarre physical vulnerability inside the inverter. So the inverter relies on an upper gate and a lower gate working in perfect opposition. One opens, the other closes.
Oh.
But when that upper gate opens with that level of extreme speed, it creates a massive localized electromagnetic disturbance. The rapid change in voltage actually forces what is called a displacement current through the physical structure of the lower gate, specifically through its parasitic Miller capacitance.
Wait, let me make sure I'm visualizing the physics here. If I think about capacitance normally, it's about storing a charge. But in an alternating current or a transient high-frequency situation like this, a capacitor will actually pass that current through, right? So the upper gate firing so aggressively acts almost like a shock wave that punches straight through the lower gate's capacitance. It's almost like a water hammer effect in your plumbing, or like a reflex, like when a doctor taps your knee and your leg just kicks without you wanting it to.
That is a perfect analogy. That displacement current is governed by the equation I equals C times dV/dt.
Okay.
So because the change in voltage, the dV/dt, is so astronomically high, the resulting current injected into the lower gate is substantial. It forces the lower gate's voltage above its threshold.
So the lower gate is essentially reflex ticking open, even though the software is screaming at it to stay shut.
Exactly.
The pure physical shock wave of the upper gate forces it open, and suddenly you have both the upper and lower gates open simultaneously.
Which is the definition of a shoot-through short circuit. You have created a near-zero resistance path directly across the high-voltage bus.
Oh, wow.
The energy from the battery just dumps freely through that pathway. The current skyrockets to thousands of amps, and the component is gone.
Melted.
Melted.
Which feeds directly into the second root cause in these specs. And this one sounds like a weapon out of a sci-fi novel. Parasitic inductance triggering an overvoltage avalanche.
Oh, yeah. An avalanche breakdown is terrifying to witness in a lab setting.
I can imagine.
When a short circuit happens, like the shoot-through we just discussed, the current isn't just high. It's changing incredibly rapidly. This is the DIT factor. Now, apply the fundamental law of electromagnetic induction to that. Every physical conductor in that system, especially the metal bus bars, has some tiny amount of natural, unavoidable inductance. We call it parasitic inductance.
Because it's not put there on purpose. It's just a parasitic reality of using physical metal to move electricity.
Exactly. You can't avoid it. And the voltage generated across an inductor equals that inductance multiplied by the rate of change of the current.
Okay.
Since the DIT during a short is so violent, even a microscopic amount of parasitic inductance multiplies out to a massive voltage spike.
So it's a bottleneck. The current is trying to slam to a halt or change direction instantly, and the inductance of the metal itself pushes back, generating this massive pressure spike of voltage.
Yes, and if the component is rated to withstand 1200 volts, and this transient spike hits 1300 or 1400 volts, the silicon is subjected to electrical overstress. The electrons are forced through the insulating layers of the chip with such kinetic energy that they physically tear the atomic lattice apart.
Wow.
That is the avalanche.
So the first two failures are pure, brutal physical interactions, displacement currents, and inductive spikes. But the third root cause outlined here shifts away from raw physics, and it gets into a catastrophic misinterpretation of reality by the control system itself, the rotor angle jump.
Right, so the inverter doesn't just blindly fire power into the motor. It uses field-oriented control, which relies on a constant microsecond perfect reading of exactly where the motor's magnetic rotor is positioned. It usually gets this from a resolver or an encoder, but the environment inside an EV is incredibly noisy. Massive electromagnetic interference, physical fretting wear on the sensor terminals, or just a glitch in the decoding chip can cause the system to misread that angle.
And the specs mention the angle jumping by 90 to 180 degrees instantly. It's like, imagine a cyclist flying downhill on a fixed gear bike. The pedals are spinning at 100 RPM with the wheels. If that cyclist suddenly tries to pedal backward, the kinetic energy of the bike doesn't just vanish.
No, of course not.
It violently snaps back into the chain, shreds the gears, and basically shatters the cyclist's shins. The energy rebounds into the weakest point.
That is a phenomenal way to visualize it. The kinetic energy of the vehicle moving at highway speed is the bike. The inverter is your shins. When that angle jumps 180 degrees, the software thinks it's applying driving torque. But the electrical vectors are now entirely out of phase. They align perfectly with the motor's natural back electromotive force.
Oh, man.
So the motor instantly transitions into an uncontrolled generator.
And it just blasts all that kinetic energy backward as electrical current.
The data here shows demagnetization currents exceeding 1,390 amps surging straight back into the system. It violently breaches the safe operating area of the power transistors. It's a complete structural failure, and it's all driven by a hallucination in the sensor data.
Which brings us to the fourth root cause. And it's almost the inverse problem of the first three.
How so?
Well, the system isn't actually tearing itself apart, it just thinks it is. And it commits a sort of electronic suicide. The documents call it desat high-frequency noise causing false lockouts.
Yes. So the desat, or desaturation protection circuit, is designed to detect a real short circuit by monitoring the voltage drop across the transistor. But remember those crazy fast, some switching speeds we talked about?
The 50 volts per nanosecond?
Exactly. That generates an immense spectrum of high-frequency noise. And through capacitive coupling, that noise can actually leak into the diagnostic pathways.
So it charges up the tiny filtering capacitor in the monitoring circuit?
Yes. The system has a hard threshold, usually around 7 volts. If the voltage on that pin hits 7 volts, the hardware just assumes a catastrophic short is occurring. The high-frequency noise can easily pump enough parasitic charge into that capacitor to trip the 7-volt limit.
Wow.
So the chip panics, it triggers an immediate shutdown, and the driver loses all vehicle propulsion on the highway.
For a fault that didn't even exist.
Exactly.
So we have these four deeply intertwined ways the system can either physically tear itself apart in nanoseconds or trick itself into a total shutdown. And human reaction time is obviously completely out of the question here.
Oh, completely.
You couldn't even realize the fault was happening before the car was dead. So how does the controller even know it's dying fast enough to do anything about it? Because the documents outline this deeply layered diagnostic architecture.
Right. So the safety architecture operates under a strict fault-tolerant time interval, the FTTI. For these ASIL D systems, the FTTI is a maximum of 60 milliseconds. That is the total budget the vehicle has to detect a fault, confirm it, and transition the entire kinetic and electrical mass of the car into a safe state.
Okay, but wait. 60 milliseconds sounds fast, but against an avalanche breakdown that happens in nanoseconds, that's an eternity. If the system waits 60 milliseconds to react to a shoot-through, there won't be a controller left to transition to a safe state.
You're absolutely right, which is why the architecture is bifurcated into two distinct timelines.
Oh, okay.
You have the software brain operating on the millisecond scale, but you have the hardware reflexes operating on the microsecond scale.
I see.
The immediate survival of the chip relies entirely on dedicated gate driver chips, like the UCC F5080 Q1 that's mentioned in the spec sheet.
So these chips sit locally next to the power transistors. They don't route data back to the main microprocessor to ask for permission.
Exactly. They cannot afford latency. The gate driver directly monitors the desit voltage we just talked about. If it sees a genuine spike indicating a short circuit, it initiates a hardware-level intervention in 1 to 2 microseconds.
Wow.
But it utilizes a highly specific technique called the two-stage turnoff.
Hold on, I need to challenge the logic of that. If the chip is actively melting, and every nanosecond allows more joule heating to tear apart the atomic lattice, isn't slowing down the shutdown the worst thing you can do? Why wouldn't the gate driver just pull the plug and slam the circuit shut instantly?
Well, because of the parasitic inductance and the overvoltage avalanche we covered earlier.
Right.
If you slam the gate shut instantly, you maximize the DIT, the rate of change of the current. You take a massive current and force it to zero in a nanosecond. The parasitic inductance in the bus bar would react to that instant change by generating a voltage spike so massive it would instantly destroy the component anyway.
You trap the energy with nowhere to go. It's like ABS brakes in a car.
Okay.
Instead of slamming the brakes completely, which would cause you to skid out of control, it smoothly pulses them to slow down without locking up. If it slammed the gate shut completely, it would cause that massive voltage spike we just talked about.
That's a great way to put it. You are caught between melting from current or exploding from overvoltage.
Right.
The two-stage turnoff navigates this perfectly. In the first microsecond, it drops the gate voltage to an intermediate level. It doesn't shut the door, it just pinches the hose.
Right.
This limits the maximum amplitude of the fault current, preventing the immediate melt. Then, in the second stage, it fully shuts off at a controlled rate, spreading out the DID so the resulting voltage spike stays below the avalanche threshold.
That is an incredibly delicate electromagnetic balancing act, and it's handled autonomously in 2 millionths of a second.
It's amazing.
But the gate driver isn't the only hardware reflex, right? There's also the hardware overcurrent detection, the OCD gating.
Right. The primary current sensors have dedicated physical pins wired straight into the logic gates of the control board, completely bypassing the software loops.
Wow.
If the sensor detects a massive physical short, that analog signal propagates instantly and physically blocks the pulse width modulation, the PWM signals.
In less than 1 microsecond, the specs say.
Less than a microsecond, yes.
Yeah.
It essentially severs the nervous system of the motor.
So the hardware flinches. It stops the immediate bleeding and prevents the chip from turning to liquid. But the car is still moving at 80 miles an hour, and the main computer still needs to figure out what just happened.
Yes.
Which brings us to the millisecond timeline, the software diagnostics.
So once the immediate hardware thread is choked off, the software has a few milliseconds to analyze the crime scene. It runs continuous diagnostic math using principles like Kirchhoff's current law.
Okay.
In a perfectly operating three-phase motor, the current flowing out of the phases must equal the current flowing back. Mathematically, phase A plus phase B plus phase C must exactly equal 0.
And if it doesn't equal 0, the current has found a shortcut. It's leaking to the chassis ground.
Right. The software monitors that sum, and if the residual current exceeds a specific threshold, it can confirm a ground short in just 2 milliseconds.
That's fast.
It is. It also monitors the internal control loops for PI saturation. If there's a slight creeping internal short in the motor windings, The proportional integral controller will have to push harder and harder to maintain the requested torque.
Oh, I see.
If the software sees the controller sitting at a 100% duty cycle for 1.1 milliseconds, meaning it's giving maximum effort just to keep the system stable, it flags a confirmed asymmetry fault.
Okay, so the hardware stopped the fire. The software investigated the math and confirmed we have a catastrophic fault. Now we hit the wall, the adaptive fallback strategy.
Yes.
Because the car is still hurtling down the highway with an immense amount of kinetic energy, and you have to do something with the motor.
The system has to achieve a safe state within whatever is left of that 60 millisecond FTTI window.
Right.
But safe is entirely dependent on vehicle speed. If you are crawling through a parking lot at under 20 kilometers per hour, the kinetic energy is negligible. The controller executes an active open circuit. It permanently shuts all the gates, the motor freewheels, and the car just gently coasts to a stop.
But at 80 miles an hour, you can't just open the circuit. The fixed gear bike analogy comes back.
Exactly.
If you just open the circuit, the permanent magnets in the motor are still spinning at like 10,000 RPM.
Yep.
They're acting as a massive generator, pushing lethal levels of back electromotive force toward an open switch.
Right. And if you leave the circuit open at that speed, that back EMF will crest over the voltage limits of the inverter. It'll blast through the open diodes and destroy the entire high-voltage bus. It could potentially arc to the chassis. You cannot isolate the motor. You have to trap the energy inside it.
Here's where it gets really interesting. You intentionally short-circuit the motor. You take a system that just survived a short circuit, and its defense mechanism is to execute a controlled short circuit on itself.
It sounds crazy, but it's called the Stepwise Active Short Circuit, or ASC. By turning on all three lower gates simultaneously, you create a closed loop strictly within the motor windings.
Okay.
The back EMF circulates through the motor coils and is dissipated as heat within the motor's mass, rather than returning to the battery or the fragile electronics.
Wow.
But doing it all at once at highway speeds would create a mechanical shock so violent it could shear the output shaft.
Hence the stepwise part of the protocol.
Right. First, it triggers a two-phase short for exactly 1.5 milliseconds. This acts as a buffer. It absorbs the massive initial transient shock wave of the demagnetization current. It lets the electrical system absorb the punch softly.
That's brilliant.
Then once that initial transient settles, it locks down into a full three-phase short circuit. This cleanly clamps the voltage generated by the motor, forcing it to stay under 720 volts, which is safely below the 800-volt battery architecture limits.
The choreography here is just staggering. The gate driver flinches in a microsecond to prevent the melt. The software calculates Kirchhoff's law in 2 milliseconds to confirm the fault. It checks the speedometer, realizes the kinetic energy is lethal, triggers 2 phases to absorb the shock wave, and then locks all 3 phases to trap the energy. All of this executes before the driver's brain is even processed that a dashboard light came on.
It is an absolute masterclass in dynamic fault management.
But you know, managing a fire is still managing a fire. Catching a catastrophic fault in a microsecond is great, but mathematically eliminating the conditions that allow the fire to start is engineering perfection.
Absolutely.
And that brings us to Section 4 of the specs, the DFMEA, Design Failure Mode and Effects Analysis. How do they architect the physical hardware to choke these physics out before they even happen?
Well, you have to stack the physical environment heavily in your favor. Let's revisit that parasitic inductance that causes the overvoltage avalanche. The DID is a given. You can't change how fast the CNT switches without losing your efficiency. So the only variable you can control is the inductance of the metal itself.
The specs mention a strict design rule here. DGPCS HW-002. It's regarding the high-voltage bus bar. It demands a highly compressed, symmetrical sandwich structure. I understand that placing the positive and negative copper plates incredibly close together with an insulator in between causes their opposing magnetic fields to cancel each other out.
Yes.
But the spec strictly mandates the resulting inductance must be under 15 nanohenries. Ideally 10. Why 15? Why not 50? Or 5? What is the physics behind that specific threshold?
It's the physical ceiling, where the math allows the silicon to survive.
Yeah.
If you calculate the maximum possible DID during a hard shoot-through, and you multiply it by 15 nanohenries, the resulting voltage spike crests at just under 1200 volts. 1200 volts is the absolute maximum blocking voltage of the SiC MOSFETs used in this architecture. If the busbar inductance drifts to 20 nanohenries, that spike hits 1300 volts, the avalanche breakdown occurs, and the chip dies. 15 nanohenries is the hard mathematical boundary between survival and vaporization.
So squeezing the physical inductance of massive copper bus bars down to 15 billionths of a Henry requires manufacturing tolerances that are almost absurd. They are literally suffocating the magnetic field's ability to exist.
And they apply that same level of aggression to the Miller effect we discussed.
Yeah.
The parasitic capacitance forcing the lower gate open.
Right.
The gate driver chip must possess a common mode transient immunity, or CMTI, greater than 100 kilovolts per microsecond.
Okay.
But passive immunity isn't enough. They implement an active Miller clamp.
Which is amazing because I was looking at this and they literally force the gate to a negative voltage, like -5 volts.
Exactly.
Instead of just commanding the gate to 0 volts when it needs to be off, the driver actively pulls it down to -5 volts when it drops below 2 volts, physically locking the door so the Miller effect can't force it open.
Oh, that's exactly right. If the displacement current from the upper gate switching punches through the Miller capacitance, it raises the voltage of the lower gate. If you start at 0 volts, any bump pushes you toward the turn-on threshold.
Right.
But by throwing a -5-volt deadbolt on it, the displacement current has to work through that entire negative deficit before it even reaches 0, let alone the positive threshold to open the gate. The physical shock wave just exhausts its energy before it can trigger the reflex.
You are building an electrical trench that the transient has to climb out of.
Exactly.
But fighting the raw power transients is only half the battle. We also have to prevent the sensor hallucinations we talked about earlier, the rotor angle jumps. The DFMEA mandates strict controls over the analog front-end circuits. They are required to use Class 1 CRG dielectric capacitors and thin film resistors.
Because the environment inside the controller under heavy load is incredibly hot, and standard components drift when they get hot. A standard resistor's value actually changes as its temperature climbs.
Which warps the sensor data.
Right. Which is why a thin film resistor with a plus or minus 0.1% precision and a temperature coefficient of less than 25 parts per million per degree Celsius is so important. It ensures that whether the controller is at -40 degrees in a blizzard or 150 degrees climbing a mountain pass, the electrical resistance remains mathematically locked. The signal to the brain remains pure.
But the hardware can only lock down the electrical signal. The magnetic realities inside the motor are constantly shifting. The specs detail a software prevention method here, a dynamic 2D lookup table to manage cross-saturation.
Yes. When you push massive torque out of an electric motor, you push immense current into the stator windings. The magnetic steel inside the motor can only hold so much magnetic flux. When it saturates, the magnetic fields warp and gleed across the direct and quadrature axes.
So even if your sensor is reading perfectly, the physical magnetic field it's trying to track has warped out of alignment.
Exactly. And if the software ignores that warping, the angle calculation drifts, and you risk sliding into that uncontrolled generator state.
Right.
To prevent this, the software runs a continuous 2D lookup table. It maps the real-time currents on both axes, mathematically predicts exactly how much the steel is saturating and how the field is warping, and actively adjusts the angle calculation to compensate. It dynamically corrects its own perception of reality to ensure it never loses magnetic lock.
If we connect this to the bigger picture, these design choices really show how automotive engineering requires treating the hardware and the software as one single breathing organism.
It really does.
So the blueprint is flawless, but a blueprint is just paper. How do we ensure every single unit coming off the assembly line is perfect? That transitions us to the PFMEA, process failure mode, and effects analysis.
The manufacturing controls have to be hyper-strict because a single microscopic flaw invalidates all the brilliant DFMEA work. Let's look at the motor stator. Before a stator is ever mated to a rotor, it undergoes 100% inline surge and partial discharge testing. They hit the copper windings with a high-voltage pulse exceeding 2.5 kilovolts.
And what exactly are they measuring with partial discharge?
They are listening for the electrical breakdown of microscopic voids. If there is a tiny air bubble in the insulating resin or a microscopic scratch on the enamel wire coating, that 2.5 kilovolt pulse will jump that gap. It won't be a full short circuit, just a tiny localized spark. The testing equipment is sensitive enough to catch electrical leakage as small as 10 picocoulombs.
Picocoulombs.
Yes. We are talking about detecting the movement of almost individual clusters of electrons. If they catch a 10 picocoulomb discharge, that stator is scrapped because that microscopic scratch will eventually degrade into a catastrophic internal short.
Exactly.
And they are just as fanatical about the silicon mounting. The SAM inspection protocols for the die attach are brutal.
SAM stands for Scanning Acoustic Microscopy. They use high-frequency ultrasound to peer straight through the physical silicon to inspect the bonding layer beneath it. Because suits and chips run so incredibly hot, traditional soldering isn't sufficient. They use a process called silver sintering, essentially fusing the chip to the cooling plate with a matrix of pure silver under high pressure and temperature. I compare this to putting thermal paste on a gaming PC CPU, but with million-dollar stakes. If that silver layer has an air void in it, it creates a thermal bottleneck. When a short circuit happens, the joule heating can't transfer through the air bubble into the liquid cooling plate. That specific millimeter of the chip superheats, the lattice breaks down, and the thermal runaway destroys the inverter.
Yes. To prevent that, the SAM ultrasonic scan looks for any discontinuity in the acoustic reflection. The automated visual inspection software mandates that the total void area across the entire centered joint must be strictly less than 5%, and no single individual void can exceed 1% of the total area.
And moving from the microscopic to the macro, the physical assembly of the bus bars is heavily automated. You can't just have an assembly line worker leaning on a torque wrench.
Because the contact resistance between the copper plates dictates the final parasitic inductance and thermal performance. They use robotic fastening systems equipped with optical character recognition. The OCR cameras verify the bolts have a specific phosphate coating to ensure a perfectly predictable coefficient of friction.
And then the robot uses a torque angle method to drive the bolt.
Yes, it doesn't just measure the twisting force. It measures the exact rotational angle of the bolt relative to the applied torque. This calculates the physical stretch of the bolt, guaranteeing the clamping force is perfect. The goal is to keep the micro-resistance of that high-voltage joint locked under 5 milliamps. If the robot detects a deviation in the friction curve, like maybe a speck of debris in the threads, the line halts instantly.
Because 5 millions of unwanted resistance at 1,000 amps generates massive localized heat.
Right.
And the final lock on this entire factory floor is the end-of-line calibration, the EOL lock.
The EOL lock is where the digital and physical worlds are finally fused. The testing machines automatically calibrate the rotor's exact zero position. This data is the absolute foundation of preventing the rotor angle jump we discussed earlier. The exact angular offset is permanently burned into the controller's memory.
And the specs indicate that the factory's overarching manufacturing execution system, the MES, oversees this process. If that precise calibration data is not perfectly burned into the memory, the MES physically disables the label printer. The system will literally refuse to print a shipping label for that serial number. No uncalibrated hardware can leave the building.
It's foolproof.
So we have mathematically flawless blueprints. We have robotically assembled hardware verified by acoustic microscopes and picocoulomb sensors. Now, it is time to try and destroy it. The final section, DVP&R, the design verification plan and report, the extreme real-world validation tests before any of this touches the public road.
These tests are sadistic by design. They follow standards like IEC 607479 for physical short circuits. They take the completed system, put it inside a thermal chamber, and soak it at 150 degrees Celsius to ensure all the components are at their maximum thermal stress.
Wow.
And then they crank the DC link voltage to the absolute maximum 800 volts.
And then they intentionally trigger the faults. Type I testing is a hard short applied before the system is even powered on. Type 2 testing is far worse. They get the inverter running at full load, switching at high frequency, and then maliciously slam a dead short across the output.
They hit it with a sledgehammer. And the benchmark to pass is absolute survival. The UCC 5880Q1 gate driver must detect the fault, initiate the two-stage turnoff, and kill the current in under 2 microseconds. The resulting avalanche voltage spike must be choked by the 15 nanohenry busbar and clamped below 1,000 volts.
Incredible.
And critically, after the fault is cleared, the system must remain fully functional with 0 secondary damage.
It has to take a direct hit from its own power supply while boiling hot and just shrug it off. But the electrical stress is only part of the validation. They also run the hardware in the loop, the HL high-speed injection tests.
Right. The HIL test verifies that 60 millisecond software response we talked about. They connect the controller to an incredibly powerful simulator that mimics a physical motor spinning at 12,000 RPM under maximum load.
And while it's screaming at 12,000 RPM, the engineers digitally inject a massive phase-to-phase short circuit and simultaneously inject a 180-degree rotor angle jump. They hit the system with a physical short and a software hallucination at the exact same moment.
It is the ultimate worst-case scenario. The system must recognize the dual fault, calculate the kinetic reality, and flawlessly execute that stepwise active short circuit within the FTTI window of 60 milliseconds. The validation criteria are intensely strict. The surge current must be caught and limited to under 550 amps.
And the torque fluctuation on the simulated motor shaft must remain under 5 Newton meters.
Exactly. Because if the magnetic field snapped too violently during the short circuit, the immense counterfields can permanently demagnetize the physical magnets in the rotor. Limiting the torque shock to 5 Newton meters proves the control strategy was smooth enough to save both the silicon and the magnets.
Which brings us to the final hurdle, the endurance trial. Catching a fault once in a clean lab is impressive, but cars live outside. They hit potholes, they freeze, they bake. I was looking at this LV214 SG4 endurance trial. It's a 500-hour nightmare. The controller is mounted to a multi-axis vibration table. They subject it to a random vibration profile with an RMS acceleration exceeding 35 meters per second squared. It is being violently hammered in every direction,
while simultaneously operating inside an environmental chamber swinging rapidly from negative 40 degrees Celsius to positive 150 degrees Celsius.
Yes.
And it's actively switching high voltage power the entire time.
For 500 continuous hours. And the validation metrics are microscopic. They monitor the current imbalance between the 3 phases. It cannot drift above 3%, proving those class 1 thin film resistors haven't shifted due to the thermal shock. The micro-resistance of the robotic busbar joints cannot increase by more than 1.2 millionths despite 500 hours of violent shaking.
It's a true torture test.
And most astoundingly, they monitor the high-speed data signals. Not a single electrical signal can drop out for more than 1 microsecond.
This raises an important question, though. How many everyday devices could survive even 1 minute of that environment, let alone 500 hours?
Half a month of violent vibration and thermal torture, and the signal cannot blink for a single microsecond. It represents an astonishing triumph of material science and systems engineering. So let's bring this all together. We started this journey inside the silicon brain of a car at 80 miles an hour. We unpacked the nanosecond physics of displacement currents and the Miller effect and the overvoltage avalanches from parasitic inductance.
Right.
We explored how microsecond hardware reflexes like gate drivers execute 2-stage shutoffs to prevent explosions, while millisecond software algorithms calculate Kirchhoff's laws to trigger adaptive short circuit fallbacks. We saw how engineering a 15 nanohenry bus bar and applying negative 5-volt deadbolts mathematically starves a fall to the physics that needs to exist. And then we walked through the literal robotic torture tests, from acoustic microscopes to 500-hour vibration chambers, to prove it all actually works.
And it does work.
So what does this all mean? It means your daily commute is safeguarded by some of the most aggressive rapid-fire physics modeling on the planet.
And the truly fascinating part is that the engineering doesn't stop here. The source documents hint at the next frontier. To truly master that catastrophic dead current spike during a short, engineers are no longer relying on physical trial and error.
Oh, really?
Yeah, they're deploying highly advanced multi-pin Python simulation models. They are building pure multi-physics virtual environments to simulate electromagnetic transients dynamically. This allows them to calculate the exact optimal microsecond delay for the soft turn-off gate resistors before the physical chip is ever even printed.
So they are mapping the quantum-level flow of electrons in software to guarantee survival in the real world. That is wild.
It bridges pure software coding with extreme physical hardware survival.
Well, if you are in the engineering space listening to this, you might want to look into how dynamic electromagnetic transient simulation tools are becoming the absolute baseline for modern vehicle safety. It is the ultimate virtual sandbox to prevent the ultimate real-world disaster. So the next time you're cruising down the highway and everything feels perfectly smooth, just take a moment to appreciate the invisible microsecond war being fought and won inside the silicon brain of your car.
A 60-millisecond race for survival, engineered to perfection.
And winning every single time.